Today's video will explain how integers are stored in memory. Hello, I'm James Helfrich. We all use integers every day. We use them for accounting or any time a number cannot be divided. The question is, how do you store an integer on a digital computer? Because you see, a digital computer is, well, it's digital, which means it only stores ones and zeros. How then do you store a number like 12 or negative 13? Well, this video will explain how that works. Computer memory can only store binary data, which is ones and zeros. Well, not even ones and zeros. It can only store charge on a chip, which we interpret as ones and zeros. And this can be thought of as a very long array of bits. So if I have 20 megabytes of memory, I'm actually going to have 80 billion bits, ones and zeros in memory, and each one starts at address 0 and continues on to the end. These are subdivided into 8-bit units called bytes, and here's a collection of bytes. And there are additionally 4 bytes in a word, and this is a 32-bit or 4-byte word. How do we turn these bits, bytes, and words into numbers? We need to assign each bit to a power of 2. So to see how this works, consider the number 1890. Here we recognize that 0 is in the ones place, 9 is in the tens place, 8 is in the hundreds place, and 1 is in the thousands place. The position of the digit determines the digit's values. In other words, 1890 is the same as 1000 plus 800 plus 90 plus 0, or 1 times 10 to the 3, which is 1,000, or 8 times 10 to the 2, which is 100, and 9 times 10 to the 1, which is 10. And it's kind of counterintuitive, but 10 to the 0 is actually 1. Okay, so we can represent this as an array of digits, 1, 8, 9, and 0, where 0 is in the 10 to the 0 space. And then I can add them all up by 1,000 plus 800 plus 90 plus 0, where I take the magnitude of the place, 10 to the third, 10 squared, 10, 1, 10, 0, multiply it by the value in that slot, and that gives me what I add up. Now, since computers are fundamentally binary, we do not use an array of digits, but rather an array of bits. And so now I'm going to say 1890, and this is the same as 2 to the 10 plus 2 to the 9 plus 2 to the 8 plus 2 to the 6 plus 2 to the 5 plus 2 to the 1. And so now I'm going to organize this as an array of bits, 1110, 11000010, where the farmost right spot is the 2 to the 0 spot, and then 2 to the 1, then 2 to the 2, then 2 to the 3. Now let's take a look at the far left spot. 2 to the 10 is 1024, and 1024 times 1, because there's a 1 in that slot in memory, that means I'm going to add 1024. Whereas on the far right, 2 to the 0 is 1. I'm going to take 1, multiply it by 0, which is in the far right slot, and that's going to mean I'm going to add 0 to that slot. Now, how do we represent negative numbers? The simple approach is to assign one of the bits to a sign value, where 1 is negative and 0 is positive. There is a problem with this approach. There are 2 different representations of 0. There is 0 and there is negative 0, which are not equal. We can solve this problem with a 2's complement. With this scheme, we store an integer as an array of bits, where the leftmost bit corresponds to the sign. If the bit is 0, then a number is positive, we can compute the values before. If the bit is 1, then things get more complicated. First, we invert the bits, called the complements, and then we add 1. For an example, let's take the negative 37. First, I'm going to represent 37, which is 32 plus 4 plus 1, and that's 37. And then I'm going to invert all the bits. So it goes, instead of going 0, 0, 1, 0, 0, 1, 0, 1, I'm going to go 1, 1, 0, 1, 1, 0, 1, 0. And then I will add 1. And that's the 2's complement. Now, the question is, why do we use 2's complement? What's the advantage? Well, reason number 1 is there's only one value for 0. In other words, we don't have this negative 0 not equals 0 problem we had before. The second, it's easy to tell whether a number is negative. Just check the leftmost bit. Third, 0 is all zeros, and that's true whether we're using negative numbers or positive numbers or anything else. I can very easily check if a number is 0. And finally, increment and decrement works the same for signed numbers as they do for unsigned numbers. What does that mean? Well, let's take a 4-bit number. Now, by the way, 4 bits is called a nibble, which is half a byte. Isn't that silly? And I'm going to say 0000 binary is unsigned 0, and 2's complement is also 0. 001, 0010, 0011. If I add these up, I get 0, 1, 2, 3, 4, 5, 6, 7. Okay, everything is good here because the leftmost bit is 0. Now, what happens when I go 1 greater than that? 0, 1, 1, 1, and I add 1, and I'm going to get 1, 0, 0, 0. Okay, for an unsigned number, that's just 8. For the 2's complement, it's -8. In other words, I wrap from 4, 5, 6, 7 to -8. And then when I increment from that, it goes 8, 7, 6, 5, 4, 3, 2, 1 to -1. Now, if I'm at 1, 1, 1, 1, from an unsigned integer, that's 15. If I add 1 to that, I'm going to get all zeros, which is 0. So I'm going to wrap around in the intuitive way. Now, if I'm -1 in 2's complement, if I add 1, I should get 0. And sure enough, 1, 1, 1, 1 plus 1 is 0. So it works exactly the way you expect. Okay, let's practice this. So take the binary number 0, 1, 0, 0, 1, and notice the subscript 2, that means it's binary, it's 2-bit. How do I turn that into decimal? See if you can solve this problem. Pause the video if you like. Okay, well, I'm going to take that number, and I'm going to put it into an array of bits. Okay, so 0, 1, 0, 0, 1. And then I'm going to assign values to each one, where the rightmost one is 2 to the 0, and the leftmost one is 2 to the 4. So 2 to the 0 times 1 is 1. 2 to the 1 times 0 is 0. 2 to the 2 times 0 is 0. And 2 to the 3 times 1 is going to be 8. So if I add all those up, 0 plus 8 plus 0 plus 0 plus 1, and that gives me 9 base 10. And the subscript 10 means it's base 10. I'm counting to 10. It's decimal. All right, here's another one. See if you can do this one too. Pause the video if you like. Okay, so I take that and I drop it into an array of bits, 0, 1, 1, 1, 0, 1, 1. And I'm going to assign the powers of 2 to it. 2 to the 6, 2 to the 5, 2 to the 4, 2 to the 3, all the way down to 2 to the 0. And then I'm going to take that power of 2 and multiply by that spot in the array, and that'll give me 0 plus 32 plus 16 plus 8 plus 0 plus 2 plus 1. And that's going to give me the value of 59 base 10, or decimal. Okay, things get a little more complicated here. Notice I have a 3-bit number here, and the leftmost digit is a 1, which means it's negative. But the question is, what is that negative value? Pause the video again to see if you can solve this. Okay, so I take that 1, 1, 1, and notice how I have the leftmost one as shaded, and that means this guy's the sign bit. It's the plus or minus. And since it's a 1, that means this is a negative number. So I'm going to run the 2's complement. So first of all, I'm going to invert the bits, and then I'm going to add 1. Now I'm going to take that, and I'm going to drop in my powers of 2, and this means 0 plus 1. And so my overall value is not going to be 1 because it was negative. It is -1. That's -1 base 10. Okay, one more example. See if you can solve this. Pause the video if you like. Okay, so I'm going to drop in the values here. 1, 0, 0, 0, 0, 0, 0, 1, 1. Okay, and guess what? Once again, the leftmost bit is negative. So that's the plus or minus sign, which means I have to apply 2's complement. So the next step is to invert all the bits. I'm going to go back again, invert the bits, see how everything changed. Then I'm going to drop in, I'm going to add 1. And now I'm going to drop in all my exponents. Oh, boy, this is actually kind of hard, isn't it? So let's see here. That's 2 to the 0 times 1 is 1, and then 0, and then 4, then 8, and then 16, and 32, 64, 128. Tally those all up, and what do you get? You get -253 in decimal, or base 10. As you can imagine, there's a lot more to this. There is how to convert numbers into and out of binary, how to do math with binary, and a bunch of other things. You can read about that in the integer chapter of the C++ data structures textbook.